Welcome to Ask and Learn.
We want to sketch the curve y is equal to x squared plus x minus 1 square rooted. So in this chapter, we have this laundry list of steps we should follow anytime we want to sketch the graph of something. So the first step being we need to find our domain. Now we know the domain of something inside of a square root needs to be restricted such that the inside is going to be greater than or equal to 0. So to do that, we're going to go ahead and factor the inside. So unfortunately for us, this doesn't factor very prettily, but if you do use like the quadratic formula, you can figure out the roots of this and see that this factors to be -1 or x minus -1 minus the square root of 5 all over 2 times, let me put another big bracket, x minus -1 plus the square root of 5 over 2, all square rooted. And so if we go ahead and set the inside of that greater than or equal to 0, we would end up getting that our domain should be -infinity to -1 plus square root of 5 over 2. Now square brackets, because we can plug this value into there, union with the other one, which is going to be 1 minus the square root of 5 over 2 to infinity, like this here. Oh, actually, those should be switched up here, the sign. So it should be plus and minus. All right, yeah. So these here should be our domain. All right. Now the next thing we're going to do is go ahead and find our intercepts. So our intercepts will be, so let's go ahead and first notice that our y-intercept isn't going to be defined since it is not in our domain. So we do not need to find our y-intercept, but at least our x-intercepts. So x-intercepts are going to be where y is equal to 0. And that's just going to be our two values that make this factor. So that tells us x is equal to -1 plus the square root of 5 over 2, as well as -1 plus the square root of 5 over 2. So those will be our two x-intercepts. Now let's go ahead and see if this function has any symmetry. Well, normally we really wouldn't think the square root of something or quadratics are really symmetric, or periodic, I should say. So let's just go ahead and check to see if this function is even or odd. So f of -x is going to be, so it would be -x squared minus x minus 1 square rooted. So that's going to be x squared minus x minus 1 square root. And this here is not equal to f of x or negative f of x. So we at least know there's going to be no symmetry, at least none about the y-axis or the origin. All right. Now the next thing we're going to want to do is to look for asymptotes. Well, in this case, we know there's not really going to be any asymptotes, but we can find our end behavior. So let's do that. So the limit as x approaches infinity of f of x is going to be So looking at the original function, we'd have on the inside, essentially it's just going to be x squared. So x squared goes to infinity, since x squared dominates x and -1 eventually. And then square rooting something going to infinity would just be infinity. And using that same logic, on the inside would just be x squared. So as x goes to -infinity, that would go to +infinity, and square root of that would still go to infinity. So we can actually say that the end behavior for this for plus or minus infinity should go to infinity. All right. The next thing we want to find are our intervals where the function is increasing and decreasing, as well as any local max or mins we may have. So to do this, we need to figure out what y prime is going to be equal to. So let's go ahead and do that on a new page. So we have y is equal to x squared plus x minus 1. And now when I take the derivative of this, I'm going to need to use chain rule. So the derivative of the outside, remember the square root is really just a half power. So this is now going to be 1/2 x squared plus x minus 1 to the -1/2 power. And then we need to take the derivative of our inside function, which is going to be 2x plus 1. So we can go ahead and rewrite this now as 2x plus 1 over 2x squared plus x minus 1 square rooted. So to find our critical values, we can go ahead and set this function equal to 0. And when we solve for that, we would get 2x plus 1 is equal to 0, since remember, nothing we plug into the denominator will ever make a function equal 0. And that tells us x is equal to -1/2. All right. Now, something else we would also want to check is where our function is undefined. So it is undefined when the denominator is equal to 0. And those were x is equal to, so I'll just say -1 plus or minus the square root of 5 over 2. But since these are our endpoints, we don't really need to worry about these being our critical values. So since they can't really be a end value, or it can't be a max or a min, since they are the endpoints. So we don't need to worry about that. But do remember, in general, we do need to check those as well. All right. So we had y prime is equal to 2x plus 1 over 2 square root of x squared plus x minus 1. All right, so let's go ahead now and actually find where this function is strictly larger than 0. And this is going to be y, so y prime is strictly larger than 0, or the function is increasing, not up, increasing on, so I just went ahead and solved this beforehand. So this should be the square root of 5 minus 1 over 2 to infinity. And we know y prime will be strictly less than 0, tells us it will be decreasing, or this would be negative infinity to -1 plus the square root of 5 over 2. So before we found that x is equal to -1/2 is a possible maximum or a minimum of this. But if we were to look at what this value 1 plus square root of 5 over 2 is, this is not in domain. So because of that, we actually won't have any maxes or mins at all. And that was probably something we should have checked in that first step to see if this was in our domain or not. All right, we have that now. And the last thing they tell us to do is to look for concavity and any inflection points we may have. So that means we want to find what y double prime is equal to. So let's go ahead and find our second derivative. So y double prime is equal to, so to take the derivative of that, we're going to need to use chain rule. I mean, quotient rule, as well as chain rule. So remember, chain rule says, so first I'm going to factor that 1/2 out front, just so I don't have to carry it around everywhere. So quotient rule is going to be, so low, so x squared plus x minus 1 times the derivative of what's in our numerator. So 2x plus 1 minus them in the opposite order, so 2x plus 1 times the derivative of x squared plus x minus 1 square rooted all over what we have in the denominator squared. So x squared plus x minus 1. And then when we square that, we should actually have absolute value in the denominator, since we know the square root should always be positive, and then squaring that. But on our domain, this value will always be bigger than or equal to 0, so we don't actually have to worry about that, the absolute values, and we can just ignore them in this case. Right. And if we go through all of this algebra here, we should actually end up with or actually, we need to take the derivatives first. So I was getting ahead of myself. So the derivative of 2x plus 1 is going to be 2x. And we already found out that the derivative of the square root of x squared plus x minus 1 is going to be 2x plus 1 over 2x squared plus x minus 1 square root. And since that's just the first derivative. All right, now if we go ahead and simplify all this algebra here, then we're going to be left with -5 over 4 times x squared plus x minus 1 to the 3/2 power. So if we were to set this function equal to 0, well, it's not going to be equal to 0, since in the numerator we only have -5. And just like before, the only place this is undefined is when our denominator is our endpoint, so we don't need to worry about points of inflection. So for this, we would have no points of inflection. And even further, we know that this here should be strictly less than 0. So our function will only be concave down. All right, so let's go ahead and write all that over here now. So our second derivative was -5 over 4 times x squared plus x minus 1 to the 3/2 power. And just like what we said before, y double prime will be strictly less than 0 or concave down on our entire domain, excluding the endpoints. So -infinity to -1 plus the square root of 5 over 2. Union -1 plus the square root of 5 over 2 to infinity. And I'll just say up here, y double prime strictly greater than 0, never. So there's no intervals for that. All right, so now that we plotted all this information, we can go ahead and actually start sketching our graph. So to start off, we have our two intercepts here and here, this one being -1 plus the square root of 5 over 2, and the other one being -1 plus the square root of 5 over 2. We're going to have no local maxes or mins. We know these should go to infinity on each side. And we know the function needs to be concave down on the entire interval. So we know, actually, so to the left of our graph, it should be decreasing. So it should look something like this, and just going off to infinity like that, keeping where it's concave down. And on the other side is going to be increasing, and it still needs to be concave down, so it'll look like this. There. So we could maybe go in and put 1 or 2 points on either side to maybe make it look a little bit better, but we've already graphed all the relevant information, so I would say we could just go ahead and stop here for our sketch.